Morning, everyone. So today we're going to start a little bit into our last chapter in IB 11, which is the chapter Unit 5 on energetics. So if you can start a fresh new page here, let's start. So Unit 5, we're going to look at the energetics of reactions. Essentially, we're going to be comparing the energy of the particles before versus the energy of the particles afterwards. We're going to try to figure out which side is more stable, why reactions will tend towards products for some equations and reactants for some other ones here. Also, the notion of endothermic, exothermic comes back in this lesson here. In which reactions do we give off heat? Do we absorb heat? We're going to look at a guy called entropy towards the end of this chapter, which is the measure of randomness or chaos. That helps us to figure out the spontaneity of the reaction. We want to see whether the reaction will occur without any outside influence. So that's sort of a gist of what we're heading into. One key thing that we're going to do today, although we are focusing in a chapter on energy, we are not looking at how fast reactions occur. So for example, rusting is a spontaneous reaction. Nobody wants it to occur, but it just happens naturally. Although even though it's spontaneous, even though it pretty much goes 100%, it's not a reaction that happens very quickly, right? The rust doesn't form overnight. It might take many, many months for this to happen. So chapter 5 is mainly about the energies of reaction. When we come back in grade 12, we're going to actually do another chapter on rates of reaction to actually figure out what the speed of reaction actually depends on. So without further ado, this is our intro to energetics. Let's start off with a little bit of background here. We're going to start off with a guy called the first law of thermodynamics. So dynamics is like sort of the physics of, and we're looking at sort of heat transfers. We will be using chemical reactions as the things that generate the heat for us or absorb the heat for us, but this is still the study of sort of the physics behind what happens to heat. The first law of thermodynamics here is essentially a statement on energy conservation. There is a few things in our world that are conserved. For example, mass is conserved, momentum is conserved. This is probably a very familiar one to you here. Energy conservation. Usually, when we say in science something is conserved, we say this quantity here: energy cannot be created or destroyed. But because the universe is a huge place, we can't study it all at once. Energy can be transferred between objects, and the nice thing about energy is it can even transform between different types. So it can change from moving energy, like kinetic energy. That energy can be stored up as potential energy. Stored energy can take the way of chemical energy. It could be mechanical energy. It could be gravitational energy. So not only can energy pass from object to object, it can also be transformed between different types. So, but can be transferred between objects. So it can be passed from place to place, or even transformed. That's not true for other things, but in this case here, transformed, and you get the idea, it's between kinetic to potential and many different types. Energy, we're going to learn in our physics courses, energy is actually a scalar. Scalars only have magnitude. They should always be positive. We'll even see specifically kinetic energy has to do with temperature a little bit later on this lesson. Because kinetic energy as a scalar should be a positive number, we're going to need to come up with a temperature scale that only gives positive numbers. Just before we get to that, however, let's just look at this energy conservation law. Let's pretend our whole universe fits inside this box here. So this one here is the universe, definitely not to scale. Obviously, because the universe is such a huge place, I'm not going to be able to do many experiments on the entire universe all at once. Usually what I do is I pick out a small fraction of the universe, again, not to scale here. The part that I'm deciding to study here is called the system. Okay? This is the part that we decide to study. It's easy in chemistry here for the system. This is generally the chemical reaction. So this is generally, let's look at the particles, let's look at them colliding, what angles are they coming in at, what bonds have to break. That is generally the system. Everything's around it, we refer to it as surroundings. So I'll just put else. So it could be us as observers making measurements, it could be outside in the hallways, outside the school, okay, it could be anywhere else around. That's called the surroundings. So, although energy conservation says it can't be created or destroyed, I want you to be able to picture that energy conservation applies to the entire universe all at once. So it says whatever happens to our universe, whatever happens in this box here, the total amount of energy can't change. And yet what we're doing here is we're setting apart. Let's arbitrarily look at just this system here. Just these particular chemicals, just this particular collision. In that case there, because I'm only zooming in, we call it locally here. I'm just looking really at a small scale. It's possible that you might have a reaction that actually gains heat. So we use Q for heat transfer term here. It's possible that the system may actually go up in energy. That may at first seem like the system has actually created energy, and yet because of energy conservation, because inside this box here, energy has to be conserved, whatever amount the system gains, we just know that the surroundings has to lose that equal amount, but opposite, and therefore the whole amount of energy in the box stays constant. Using a money analogy here, I can have what's called an exothermic reaction. My system may actually lose energy. It may actually minus a Q. Notice I'm using Q as heat this time. I'm not using it as charge like in earlier chapters. But let's use a money analogy. The system pays the surroundings $20. So the system seems to have lost 20 joules. It seems to have disappeared. And yet, because the surroundings has actually gained 20, we know that the total amount inside the box here is totally unchanged. So in that case there, we can have a local transfer. That's why we can have endo and exo. However, we know inside our whole box, inside our universe, it is actually conserved. Physicists say our universe is constantly expanding. So even if this box here is constantly stretching outwards, the total amount of energy is always going to be fixed. That's what physicists refer to as the general heat death of the universe. So eventually when we fast forward the clock, the energy will be so dissipated, it will be so spread out, basically no work can be done anymore. So it paints a very depressing picture. Let's just have a look at different types of systems here. For our systems, for our chemical reactions, we can set up our system in what's called an open system. As the name suggests, an open system here is one in which matter and energy can escape. So if I just draw a picture of an open system here, that could be as simple as, let's say I'm doing a dissolving reaction. I have some powder down here. I drop it in a bunch of water. In this case here, because there's no cap on top of it, if this reaction in particular, if it forms a gas, those gas particles are free to leave. There's no cap, there's no lid keeping the gas particles around. Similarly here, glass we're going to find is not a really good insulator. It doesn't trap heat very well. So not only am I going to have lots of heat loss to the environment, I will also get sort of energy transfers, heat loss out the sides of the container as well. So that's an open system. Matter and energy can escape depending on what the reaction actually is. Let's switch over to sort of the medium case here is, let's do a closed system. A closed system, we're going to put a cap, we're going to put a lid on top of it to try to keep the matter constant. So in this case here, we're going to say matter cannot escape, but energy still can. And in chemistry, we use both open systems and closed systems. It depends on how you want to set up your system. In this case here, it can be as simple. It can be exactly the same particles dissolving the same reaction here. But in this case here, we're going to put a lid on top of it. Put like a watch glass on top of it. Try to form a tight seal so that especially if your reaction happens to produce gases, those gases are still stuck around. Next year, we're going to do a chapter on equilibrium. Equilibrium relies on the reactions being able to go forwards as well as backwards. If the forward reaction generated these gases, I'm going to need the gases to stick around to potentially reform the dissolved particles here. I would definitely need a closed system for equilibrium next year. However, in this case here, I mentioned glass is a fairly good conductor here. Energy can still escape, probably can escape through the lid as well, but energy can escape through the sides of the container. For this stuff here, we're going to be assuming a perfect world. We're going to try to get as close to what's referred to as an isolated system. Just looking at the pattern there, right? We want matter to stick around in case I have equilibrium. In this case here, I want to mimic a system that both energy and matter can escape. So an isolated system here, let's just put here matter, matter and energy cannot escape. We want to make sure we trap all the particulate matter. We want to trap all the heat transfer inside so that truly whatever energy is inside the system, it basically stays inside the system. It's just stuck inside. You can imagine here we can mimic it with a really heavy-duty thermos. Instead of a glass beaker, which is nice and conductive here, if I put the outsides made of something, maybe I'll draw another picture of this. If I make the outsides like a thermos kind of material, You put some boiling water in it in the morning time. A thermos might be able to keep that water really, really hot for the better part of the day, maybe 10 hours, 12 hours or so. But eventually, even this isn't perfect. Even if we have hot steaming water inside here, over time, if you leave it a couple days, this one here will definitely have transferred heat. But we're just going to mimic that here. We're going to pretend we're in a perfect world. We're going to pretend we're perfectly isolated. So depending on how you want to set up the system, it could be open, it could be closed, it could be even isolated. Just before we sort of introduce our main term for this chapter here, a couple other definitions for you to know. One is the notion of internal energy. When we describe these systems, it doesn't matter the type of system, we can have something called internal energy. For some reason, we're going to use the capital letter U for it. So in this case here, internal energy, as the name suggests, it's the energy that's internal. It's the energy that's inside the system. In some sense here, internal energy is the total energy of the system. Turns out this quantity here in general is really hard to measure, because if you imagine here, let's take a system. There's going to be way too many particles for you to deal with. There's going to be way too many ways energy can be stored. There's no real exact way of getting this number. Let's just do a really sort of simplistic example. Let's say we only had 3 particles. One particle happens to be traveling really slow. I'm going to give it 10 joules of energy. Joule is going to be our unit for energy. So 10 joules, let's say that's the kinetic energy. This second particle here is traveling at some medium pace. Let's make it 20 joules. The higher the energy amount, right? If this is kinetic energy, I'm going to tend to move faster. And let's have one particle that's sort of zipping around here, a really fast moving particle at 30 joules. So my simplification this time is I only have 3 particles. In reality, there's going to be moles and moles of particles. But in this system here, if I only have 3, I'm only having to go up to each particle. I'm going to go to the slow particle. Oh, you have 10 joules. The medium particle has 20 joules. The third particle here is 30 joules. I'm going to be able to just add them up, and I'm going to say 60 joules. Again, pretty simplistic, but I just want to give you an example of what internal energy is. I'm also only focusing so far on kinetic energy. There would technically be maybe some London forces, potential energy between the terms, especially as they collide on each other. There's going to be some transfer of energy as well. I'm totally ignoring all that. I'm just focusing on kinetic energy. What I want to make a sort of parallel with here is internal energy. Let's compare it to temperature. That's another scale that we use a lot in this chapter here, because temperature is some measure of heat, is some measure of kinetic energy, the speeds of particles. In this context here, temperature, we're going to use capital T for it here. Temperature, like internal energy, it also measures the energy of the system, but unlike giving it a total, temperature is actually a measure of the average energy of the system. So, based on my same number example here, I can say, sure, you have 60 joules total, but that 60 joules is on average split among 3 particles. It's sort of like each particle on average is going 20 joules. And if I stick a thermometer inside there, whatever my temperature reads, 10 degrees, 15 degrees, whatever that is, that temperature number is actually an average measure of the speeds inside the system. Even though temperature does do an average, even though the average is 20, I'm going to be assuming majority of particles are traveling 20. There will always be some that are slower, some that are faster. So that's sort of the distinction between internal and temperature here. We refer to internal energy as an extensive quantity. If you look back way back in our first chapter here, extensive quantities depended on amount. So depending on how big of a system, depending on how many particles make up my system, let's say instead of my container having 3 particles, let's say it has 300 particles. If I go up to each of the 300 particles, they may on average still be moving at the same speed, but because I'm having to add up a whole bunch more particles worth of energy, this number here will go way up. But in the temperature example here, let's say this is the sort of container inside my fume hood. My thermometer inside the fume hood on a warm day, it says 15 degrees. I pull my thermometer out into the main classroom. Way more particles, right? Internal energy goes way up, and yet my thermometer itself stays reading the same 15 degrees I said earlier. In that case there, it's because, you do have many more particles, you do have way more internal energy, but you will also have more particles to carry that energy. On average, your temperature reading hasn't changed. So in temperature here, if you want to sound fancy, temperature here is an intensive quantity. This one here does not depend on amount, because we've taken an average. Not that temperature can never change, but in the example that I just described for you, just because you have more particles doesn't suddenly mean you're going to be necessarily faster. In terms of temperature here, we have 3 main temperature scales. So we'll start off with the one we do mainly in Canada here. We do degrees Celsius. Because water is a really common chemical for us, we choose the 0 to be the melting point of ice, or you can call it freezing point of water, depending on which way the heat is going. I'm going to set 100 to when water starts boiling. Notice water implies that it's already a liquid. I'm going to chop that up into 100 little segments there, and that's how I actually get my degrees Celsius. However, because water is just some random chemical, we will have some Celsius readings that are positive, some Celsius readings that are negative. Let's cross the border here and compare over in the States. They typically do degrees Fahrenheit. They do something very similar to us. They do melting point of ice here. They set that at 32 degrees Fahrenheit. If you're a baker, 100 in terms of degrees Celsius is 212 for Fahrenheit. We look at the States and be like, wow, you're weird. Why 32? Why 212? They could equally well say to us, well, why 0? Why 100? But what I want to show you here is it's completely arbitrary. They did the sort of little divisions between there. They will eventually hit a point where even Fahrenheit is equal to 0. It's just not so much for water. So same sort of problem is for Fahrenheit. We can have positive Fahrenheit. We can also have negative Fahrenheit. Like I've already mentioned here, energy is supposed to be a scalar. Scalars are only supposed to be just the size, just a positive number. It shouldn't ever go into the negatives. In fact, temperature, if you go into science, temperature is sort of proportional to the kinetic energy. It's proportional to a term that's always positive. So these 2 temperature scales here become a little bit problematic because my temperatures may actually drop into the negatives. So what we do in science here is, whether we're in the States or whether we're just in Canada and doing Celsius, we've created a new what's called an absolute scale. That absolute scale here you've heard of before. This is called the Kelvin scale. And basically what we did is we took the 0. Instead of putting the 0 arbitrarily for water or randomly where the Fahrenheit is, we're going to actually reset our 0 to the absolute coldest temperature, okay? No, that's 0 Kelvin, okay? And that one there, we're going to call that absolute 0. We're going to call that the absolute coldest temperature anything can get to. We're basically going to rescale it. Since that's the coldest, that's going to be 0. We're going to eventually get everything all positive. Fortunately for us, because we had a bunch of the Celsius scale was already used really commonly here, we're actually going to preserve the number of tick marks here. Turns out when we reset it, we actually need to reset it by negative 273. If you want to be really precise, you can say 273.15 if you like. So if it was 273 steps going down to absolute 0, that would be the same 273 steps to go up. So 0 degrees Celsius would then be 273 Kelvin. 100 above that would then be 373 Kelvin. Notice they don't say degrees Kelvin, but we've definitely sort of solved our problem. Now that 0 is actually at the absolute coldest temperature that we're at, then all the temperatures are now therefore going to be positive. So that's going to be proportional to the kinetic energy, which is scalar, no problem. How do we actually get this absolute 0 here? You actually need to look back in our gas laws lesson. If you look up a guy called Charles's law. So I gave you a nice handout with some of these graphs here. Just to repeat here, for Charles's law here, he was doing volume and temperature kind of readings. He would take balloons here. He would start off, let's say at room temperature, he'd measure the size of his balloon. He'd say, I'm at room temperature, here's the size of my balloon. He'd slowly cool this down here. Remember, for the gas laws, we had these 3 sort of variables, P, V, and T. For the gas laws, Charles decided to keep pressure constant. That's actually more common than you think here. We're always under roughly about 1 atmosphere pressure. So all of our experiments have been done under constant pressure. Later on, this will be called Gibbs constant pressure. But basically what he did is, under constant pressure, he cooled down his balloon. We would assume the particles here are a little more sluggish. The balloon is stretchy. It can sort of respond to that here. Because the particles can't move as quickly here, a little bit less temperature, a little less size. A little less temperature, a little less size. Because these are gases here, even if you drop into the negatives, the balloon will still probably have some positive volume. But what he found was a nice proportional relationship. He ended up getting a nice straight line fit. He did that for gas number 1. He may have done that again for gas number 2, maybe a different gas, maybe a different number of moles inside, different sort of readings inside, and yet for some reason, everything seemed to extrapolate back to some uniform temperature. And in that case, basically the idea was, here's how cold balloons have to be so that the particles are moving so sluggishly that the balloon is basically a point particle. And that's actually where he found this is just extrapolating here. The Kelvin temperature is Celsius and is offset by 273. That is a relationship that hopefully you know already. These graphs so far are representing linear graphs because the slope is constant, but what we prefer is we actually like a proportional graph. We like there to be no y-intercept. So if I then definitely do reset the 0 here, that's why for Charles's law, if I had converted temperature to the absolute scale, then it's definitely proportional. Then it actually goes through 0, 0, and then I don't have any y-intercept to worry about. So in chapter 1, that's why we defined everything. Make sure everything is put back into the Kelvin before you do any other math. So that's fortunately for us here, absolute 0. In science, we've gotten fairly close to absolute 0. We've gotten, I believe, to like a micro Kelvin, so it's like 0.000001 Kelvin. In that case there, we're getting so cold that any amount of heat that I manage to pull out, it just goes right back in. Fortunately for us here, we're going to see a formula tomorrow. Q is mc delta T. We're going to be looking at changes in temperature. Because the number of steps is going to be the same as the Celsius scale here, we'll just make a note here. Temperature increment is the same for Celsius and Kelvin. So although Celsius is not the same as Kelvin, if you just really match it up here, 0 degrees actually matches up with 273, 100 matches up with 373 here. If my formula doesn't really care what the exact starting temperature or final temperature is, and if it just cares the difference, if I ask you how many steps between 0 and 100, you'd say, oh, that's up by 100 steps. Even though the numbers are different, they're now 273 and 373, I can similarly say it's up by 100 steps. So the number of increment, the size of that increment here doesn't change, so therefore we're going to see us a little bit sloppy on the next lesson, compare Celsius and Kelvin. Oh, they're the same. Lastly, I'm going to introduce to you our main term for this chapter here. We're going to use some of that background here. This next term here has a lot to do with internal energy, and this is the guy we're going to spend about 2 weeks' time looking at. We're going to do a guy called enthalpy. We're going to use capital letter H for it. E is in general just energy, so H specifically looks at enthalpy. Just like internal energy was the total amount of energy, all the different forms, for enthalpy we're going to focus in just merely on the heat energy in the system. Energy that is actually in the heat form, in the form of sort of the average kinetic energy, and also focusing here, this is just the energy that's inside the system. The universe is way too big a place to study. I'm not going to bother trying to capture all the heat in the universe. I'm just going to say, well, you are these particles here. Maybe let's do this as an experiment. Let's say I have some powder again here. I would go up to each of the particles. I would go up to the liquid around it. I'd add up for every particle. Here's the energy you have. Here's the energy you have, specifically looking at the heat type. And I'll give you that total number. Just like before for internal energy, that should be an impossible task because there's way too many particles to actually deal with. There's also way too many different forms to deal with it. So let me just make that note here while I have it here. Absolute, so an exact number for enthalpy can't be derived. So absolute enthalpies cannot be determined. No matter how good our science gets in the future, technology gets in the future, we can never get a handle on so many particles and so many different ways energy can be stored. Fortunately for us, though, what we care is, while I might not know the starting number, nor I might not know the ending number exactly what your total is, because in chemistry we're interested in going reactants to products, I can focus more so on a relative enthalpy. I can focus more on a change in enthalpy. Do you have more heat now or less heat now? Although I don't technically know what the number actually is. Absolute enthalpies cannot be determined because there are too many particles, way too many. You need to go up to each particle one by one. Don't double count any particles. Way too many particles and too many ways energy can be present. Okay, it could be kinetic energy, it could be stored energy, it could be many different types. But fortunately, like I mentioned, in general for us, we're going to have a chemical reaction. The particles in the reaction actually make up our system. We want reactants in becoming products. Again, reminder, we do want to see an arrow instead of equal sign, even though you're balancing later on. What I'm saying here is perhaps we may have, if I plot this sort of enthalpy diagram, just think of enthalpy here as energy, but specifically here it's the energy in the system. Sometimes this graph here, this is called a reaction coordinate. Sometimes you put just reaction on this axis. And if this is a reaction coordinate or a reaction axis, all we're saying here is we would expect reactants more so on the left and products more so on the right. You could also say time if you like. You can say, well, this is at the beginning, we were all reactants. As you go over, you can say time as well. I prefer reaction coordinate later on because in chapter 7, in grade 12, we're actually going to do reverse reactions. It's a little bit hard to think about going back in time, running the clock backwards, but it's okay to say, well, reverse reaction would just be products going to reactants. So in this case here, I may have, there's going to be chemical A is my reactant, or like whatever equation that we're looking at. It's a question mark. I have no idea what the starting amount is. There's way too many particles in A. There's way too many ways energy is stored as well. And yet over the course of the reaction, as some bonds break and as some bonds form, we're going to end up having some relative change in enthalpy. I'm going to have chemical B here representing my products here. Again, there's a question mark. I don't know exactly what this number is. I can't tell the absolute enthalpy. But what I can do is I can do the change. I can say as the reactants have steadily become products, how much did your enthalpy change by? What you're going to do is you're going to extrapolate this reactant line over. This line here ends up going upwards, and we're getting our main term here. This is called the delta H. Delta H here refers to an enthalpy change, or change in enthalpy. So this is a little bit weird here. I might not necessarily know the starting number or the ending number, but what I can tell you here is I can tell you at the end of the day, I have more energy than before, because change is always final minus initial, right? H final minus H initial. Again, even easier in chemistry here, final is always products. So we're really looking for H products minus H reactants. We're looking for the relative as the reaction has occurred. Do I have more energy or do I have less energy? In chapter 5, we are mainly focusing here on just start and finish. We're going to see a law later on that says, I don't really care about the in-between. We're going to come correct this picture a little bit more next year. And basically, we're going to say there's actually an energy hill in between. And that energy hill actually describes the rate of reaction. Okay? But focusing mainly in this chapter here, we're looking at start and finish. I don't really care what's happening in between. Hopefully, this seems a little bit common to you here. If I have a reaction, at the end of the day, it's actually stolen energy. That means heat has actually entered the system. In that case there, we're going to refer to this type of reaction here as an endothermic reaction. So endothermic, the heat enters the system. You can also use terminology like heat is absorbed. So what's happening here, let's take a test tube, let's do a dissolving reaction, and basically heat enters the system. It's going to look my system. Remember, my system are the particles, my system are the collisions that are occurring here. It looks like my system has gone up in energy. It looks like conservation energy doesn't apply anymore, and yet we're going to realize no matter what type of system, the only reason why the particles have been able to gain energy is because the surroundings has lost equal and opposite energy. So in that case there, we're going to have endothermic heat entered the system. A couple of ways of showing it here. I already showed it to you on an enthalpy level diagram. This time I do enthalpy in time here. I start out somewhere low with reactants. I end up somewhere higher. Again, we're focusing mainly on start and finish. If I want to give you a delta H term, a change in enthalpy term, delta H would have been what's your enthalpy of products minus what's your enthalpy of reactants. I don't know exactly these starting numbers, but I do know because this number, bigger number minus small number, that delta H here is going to be positive. Positive delta H is one good way of telling you that it's endothermic. The other good way here is, let's say this is reactants and these are products. Which side should the heat term be on to show you that heat is actually entering? Hopefully you're able to say to me that the heat term, they can even say plus heat or even plus energy, just to be a little more generic. If the heat term is on the left-hand side, it also means endothermic. At first, when you look at that, you'll be like, why? This side, because there's a heat term, it looks like that side's actually hotter. But in this case here, if you actually think about the reaction, the reactants steal a bunch of heat that was just loose in the environment here. The reactants gain this heat, store this heat. As they become products, I don't see any other heat term, and basically that means then the products have sort of locked away all that heat inside of it. That's why products end up being higher energy. Using energy arguments in chapter 2, chapter 3, we're going to prefer the side that's lower energy. Lower energy implies more stable. So even though this reaction might still happening, we actually prefer, in using an energy argument, we prefer to be on the left-hand side for an endothermic because it's lower energy. Now here's the thing. Heat is actually entering the system. Let's imagine I grab this test tube here from the outside. My question here is when I'm grabbing this from the outside, let's make sure I have 5 fingers here. So 5 fingers are holding this test tube. My question is, do I end up feeling hot or do I end up feeling cold? The thing you need to focus on here is, we're focusing on this graph here, we're focusing on the particles in the system. We're focusing on the little dots themselves actually gaining energy. They're actually gaining energy and in fact stealing energy from me. So what's happening here, my body temperature is about 37 degrees or so. As the reaction actually pulls away heat from my hand is just generally going to get colder and colder. So in this case here, what we feel is actually the opposite. Let me make a note here. We are always surroundings. We are never small enough to actually be the system itself. We are always surroundings, so we end up feeling colder. Anytime they imply, oh, the temperature drops or whatever, it implies that we are surroundings. We can never have a temperature or a thermometer that's so microscopic that can actually measure what the particles are doing, right? So if an endothermic reaction is happening here, we're going to end up feeling cold from the outside. Sometimes people get tricked then. I say, okay, sure, our hand is outside the beaker here. Yeah, we feel cold because the heat is actually leaving. What happens if I take my finger again? And what happens if I dunk my finger into the system? Do not say it suddenly feels hot. Imagine you go to McDonald's and you buy a cold pop. If it feels cold on the outside, it's definitely cold on the inside. How come? I just said the system actually gains energy. Even if you stick your finger physically inside this liquid here, the particles themselves are still too microscopic. They're still colliding around your finger. They're still pulling energy away from your finger, so you're still going to feel cold. So all that to say here, we are never going to be small enough to be system, so therefore we have to just sort of infer whatever that happens to me. If I feel cold, it's because the system internally has gotten hot or has gained energy. The opposite of this one here would be an exothermic reaction. For an exothermic reaction, you can say heat exits the system or heat leaves. So energy would be a negative number because we're now losing energy. But overall, the universe is conserved because the surroundings has picked up that energy. 2 ways of showing exothermic here. I may have chemical C becoming chemical D. I'm going to spit off an energy term here plus energy. This means as C becomes D, chemically speaking, it ends up releasing off energy. This energy is now free to go. That's the energy that actually leaves the system. We're going to spend about a week and a half, 2 weeks or so actually finding 6 or 7 different ways of figuring out how much energy this is going to be. But nonetheless, for an exothermic, it should be always plus. Sometimes for a multiple choice, they try to trick you and they try to put like a D minus energy. If really there was supposed to be a minus, I could have just plus the energy on the other side. It's either plus on the left side, endo, plus on the right side, it's going to be exo. So in this case here, they can give you plus energy. They can even give you a number, so let's say plus 15. Usually these are going to be quoted per mole, so it's going to be in the kilojoules. They might just say kilojoules, but it's understood that every time you run the reaction, let's say I run this reaction once here, it ends up giving off 15 kilojoules every time I do that. Let's look at enthalpy level diagram here. So we're going to have enthalpy. Right, so we're going to have H against the reaction coordinate. What's going to happen is I don't know what chemical, like how much energy, what's the enthalpy C actually has, but I know that by the end of the day when C has become D, we end up releasing a lot of energy to the surroundings. Again, there's going to be an energy hill that we'll come back to next year, but this change in energy, I'm going to still prop my reactant line over. This is now delta H. Delta H is still always going to be products minus reactants. In this case here, I'm going to take a smaller positive number minus a bigger positive. Delta H is now negative. So those are the 2 ways to tell it's exothermic here. Gives off heat, delta H negative, or the heat term is on the right-hand side. So that's an exothermic reaction. If my system here, it could be another dissolving reaction. Some of these are endo, some of these are exo. The particles themselves are actually giving off heat. The particles themselves are actually losing this energy. And here I am kind of holding this on the outside. And what I'm going to do is I'm going to end up feeling all that heat outside. We who are surroundings get hotter. Or we're going to feel all that heat that actually comes off of it. So there's a nice little memory aid here. You can say an endothermic reaction, heat enters. or you can say for an exothermic reaction, heat exits. Let me just do one example with you here. If you remember that magnesium burning demo that we did back in chapter 1 here, the reaction was magnesium and oxygen becomes MgO, right? Synthesis reaction, we need to balance it, right? This one here was the one that gave off a really intense white light, so we know it's very, very exothermic. A lot of it's being released as light energy. In this case here, I actually happen to know this number here. The energy, again, we're going to spend a lot of time focusing on what this number is going to be, but for this reaction, it's actually 1200 kilojoules per mole. That means every time you run this statement, you end up releasing off 1200. But the question here is, what is this per moles of? We're going to see this time and time again over this chapter. It's going to be moles of reaction. Every time you do this statement. So for example, in this statement, every time you do the statement once, it only takes 1 mole of O2. So for every 1 mole of O2, we end up releasing 1200 kilojoules released. Because I ran that statement once, and there was actually a 1 there. If I react 2 moles of O2, well, for just running the statement once, I get 1200. If I do 2 moles of O2, then that's going to be double that, right? Every time I run 1 mole of it, I get 1200. But what about the mole ratio here? What about this one here being 2 moles Mg? Well, again, if I run the statement once, I get 1200. That statement once actually needs 2 moles. So I can actually say for every 2 moles of magnesium, I only get 1200 kilojoules. If I only use, say, 1 mole of magnesium, just giving you a feel of this one here, well, running the whole statement once gives you 1200. That's what I mean by moles of reaction. Because I'm only going to react 1 mole of the 2 that I need, this is only going to release 600. It's always going to be released, but everything is in a nice ratio for sort of how many statements do I run. So just a little bit of stoichiometry comes back again. Not too much, but hopefully it's a little bit easier this time around. I want to tell you here, when, let's say, 5 grams of magnesium are burned, let's figure out how much energy is released. Since I know every time you run this statement, every time you run 1 mole of reaction, it ends up releasing 1200 kilojoules. So what we're going to do here is I'm going to say question mark Q. Q is going to be my sort of generic energy term. We'll see this more in the next lesson. We're going to start off with 5 grams. Unfortunately, my energy term here is in relation to moles, so I need to convert grams to moles first. So going to your periodic tables, I believe magnesium is 24.31 grams per mole. That so far is grams of magnesium, because the thing that I'm burning happens to be magnesium. Technically speaking, magnesium, like moles of magnesium, is not exactly this unit yet, but you can now use the mole ratio. You can say when there are 2 moles of magnesium, that's like running the reaction once. 1 mole of reaction. Every time you run this statement, you get 1200. And it's actually that statement at the end that we then go, for every 1 mole of reaction, we end up releasing 1200 kilojoules. You don't need to worry about positive negatives because I can just say in words, here's the amount of energy. I know it's exo. I know it gets released. So 5 divide 24.31 divide 2 times 1200 gives me here a positive number, 123. The units all canceled out except for the kilojoules at the end of it, and then I can just say in words, 123 kilojoules was released. The system has lost 123 kilojoules. Wait, I thought it was 1200. It's 1200 if I react a whole mole, but in this case here 5 grams is not even a mole yet. It's a little bit cumbersome. I know this part here looks a little scary. Why moles of reaction, things like that. It's a little bit cumbersome to write that in 2 steps. So usually what we do instead is we say 1200 kilojoules per 2 moles of magnesium. I sort of imply, yeah, I know how to read this statement once. Reading this statement once is not only 2 moles, it also is 1200. So there's that 1202 moles. All right. So if you have any questions, just let me know. We'll go from there. Thanks, guys.